Hi, my name is Lekha Patil, and I am in my second years at the Master's in Mathematics program at San Francisco State University. Today, I will be talking about the Hausdorff dimension of totally disconnected thin fractals with very thick shadows. When you hear about a fractal, you should think about a repeating contraction. For example, with this snowflake, wherever I zoom in, I will see the exact same snowflake. Fractals may be self-affine, which means that they contract at different rates in different directions. For example, a square contracting into a smaller rectangle, or they may be self-similar, which means that they contract at the same rate in every direction. So a square contracting into a smaller square. When you think of dimension, you may think of square having dimension 2, a cube having dimension 3. Fractals are interesting because oftentimes they have a fractional dimension. So 3 halves, log 5 over 6, etc. I'm interested in seeing when a fractal has a very thin dimension, does it have projections in every direction that have maximal dimension? This all began with the Mendivil-Taylor fractal, which Mendivil and Taylor constructed in 2008. This is a totally disconnected fractal that projects very thick shadows in every direction. And with a little bit of work in 2022, we were able to show that this fractal also has a dimension arbitrarily close to 1, despite living in the 2D plane. Unfortunately, it's difficult to calculate the exact dimension because it's a self-affine fractal, which motivated us to construct a self-similar solution of such a fractal. And so this led to our corner and cross fractal, which projects very thick shadows in every direction and has dimension arbitrarily close to 1. We also were able to develop a classification of which fractals have very thick shadows in every direction. To illustrate the theorem we developed, I'm going to focus on this third condition. We know our corner and cross fractal has very thick shadows in every direction because any subset that I take, when I take the convex hull of the remaining subset, it will intersect the convex hull of the initial subset. For instance, I took the convex hull of this rectangle and it intersects the convex hull of the remaining rectangles in cross. This is true for any possible subset I take because it always reduces to the convex hull of one of these rectangles and the convex hull of a cross, and there will be this intersection right here. This led us to inquire whether we can generalize these totally disconnected fractals to living inside any polygon, and indeed we can, because of this triangle right here. This triangle projects very thick shadows in every direction, which we know because the convex hull of this triangle, of any pair of these triangles, will intersect the third triangle, and we know that this Hausdorff dimension will get closer and closer to 1 as we reduce the base. Because polygons are just finite unions of triangles, we can insert this fractal into any polygon we want. Thank you to the ARCS donors for all of your support.